Hello, this is Jack Jackson. Today we're going to be going over practice test 3 from college algebra, 3A, and I'm going to actually break this up into probably some multiple videos, so we'll do a few questions on each one. I just went in and saved this test with no answers so that I could go to the review and all the correct answers would be in the test already, so we can sort of check it against the computer as we go along here. So we're just going to go through here and work each one of these, as we go here. So the first one, 65 u to the negative 12 v to the 17th over 30 u to the 6 v to the negative 4. What we're supposed to do here is divide and simplify. What they're wanting to do this is have positive exponents, which is what they say here. One of the tricks is to take the constants and break them down into prime numbers. So I see I can divide a 5 out of this. So that's 5 times 13 for 65. But 5 and 13 are prime. 30, when we break it down, I can see that's 3 times 10. 10 is 2 times 5. So this is 2 times 3 times 5. Now, let's make all the powers positive. U to the 6 is already positive power, so we leave it where it is. U to the negative 12 flips down the bottom and becomes U to the positive 12. V to the 17th is already a positive power, so it stays where it is. This v to the negative 4 flips up to the top and becomes a positive power. Now, we take care of things sort of one at a time. 2, nothing to do with that. Same way for the 3, but the 5's will cancel out. 13 stays in the top. In the bottom, I multiply these together. I keep the base and add the exponents, so that becomes 18. 6 plus 12 is 18 for the power. And similarly, we get 4 plus 17 is 21. And finally, go ahead and take this 2 times 3 is 6. And so we should get 13 v to the 21 over 6u to the 18th, which is exactly what they have. Let's go on to problem number 2. Okay. Similar kind of problem. We were working with properties of exponents here, and we want to just simply simplify this using positive exponents. So a couple ways to do this, but let's work here. This is 3 to the 4th, x squared to the 4th. This is 4 to the 2nd, and x to the negative 2 to the 2nd. I'm going to leave this just 3 to the 4th for the moment. This is x to the 8th, because I multiply powers here when I have a power to a power. Let me just leave that 4 to the 2nd for a minute. And this is x to the negative 4. Here I can add exponents. 8 plus negative 4 is x to the positive 4. 4 squared is 16. 3 to the 4th, okay, 3 to the 4th is 3 squared times 3 squared. That's 9 times 9 is 81. Now I need to take 81 times 16, and I'll just multiply that out a long way. 6 times 1 is 6. 6 times 8, 48. And then 1 times 81 is 81, but it's really 10 times 81, so that's 810. Add. So that's 1296. And then I have x to the 4th power, and that's exactly what they have there. Problem number 3. Alright, 42 x to the 14th, y to the negative 7th, z to the 9th, over 14 x to the 7th, y to the negative 4, z to the 3rd, all the negative 2. So I'm going to work this one. I'm going to leave this negative 2 power on the outside, work inside for a minute. 12 is 2 squared times 3, 4 times 3, so it's 2 squared times 3. 14 is 2 times 7, so I've broken those down into prime numbers. I'm going to make all the powers positive inside the fraction here. So these on the y's are both negative, so they flop over here like this. And these on z are positive already, so they stay where they are. So I've just broken down the constants into prime number, product of primes and prime factorization, and I've made all the powers positive. If they're negative powers, I've flipped them over. Now the negative 2 power on the outside, just leave it alone for the moment. Now we go through and combine or cancel things that we have here. So 2 squared over 2 to the first, that one of those 2's cancels, leaving the other 2 in the numerator. The 3 and the 7 don't cancel, so they stay where they are. The x's cancel out. 7 of these x's cancel with 7 of those, leaving x to the 7th in the top. Subtract exponents. 14 minus 7 is 7 there. 7 minus 4 is 3 for the power on y, but that goes in the denominator. Similarly, we get z to the 6th in the numerator here, 9 minus 3 for the power. Now, I've done about what I can on the inside here. I'm going to change this to a positive power, and that's going to flip what it has hold of, which is the entire fraction. Like that. And now I raise everything. Since this is all multiplication, I can, well, this is division of course, but within that is multiplication. I can raise every factor to the second power. Okay, let's see what we can do with that. 7 squared is 49. 2 squared is 4. 3 squared is 9. Y to the third to the second, we multiply the powers here and get y to the 6th. Here we get x to the 14th. Here we get z to the 12th. We're again multiplying the powers there. And then we go ahead and put the 4 and the 9 together to make something's wrong here. Oh, I said 12 and it's actually 42. I don't know why I did that. Okay. 42 is 2 times 21, 2 times 3 times 7. Alright, so we got a little bit of a problem there. Let me see if I can fix that. How I got 12 there. Okay, so let's see if we can fix that. Okay, so what does that do to us? Well, the 2's and the 7's cancel all together, and the only thing that leaves now on the constants is the 3. So it's actually a little bit easier there. So, see, all this is gone. And when I flip it over, the 3 goes to the denominator. And then I square the 3, but these guys are not there. So, this is gone. And so the only thing actually there is the 9. So actually that's the final answer there. And that does check with what's over there. Okay. Alright, that's the third one. Let's go to number 4. Okay, the square root of 448. Okay, well, the trick here is the key is to break this down into prime numbers. Now, this is a little bit bigger number, but I think I can clearly see that a 4 is going to divide into there evenly. 1, 1, 2. Well, 4 is a 2 square. So that's down into prime numbers. Looks like I can probably get another 4 out. One way you can check to see if a 4 will divide evenly into a number is just look at the last 2 digits. If 4 goes into that evenly, then 4 divides the whole thing evenly. So 12 divided by 4 works out. So this should work out nicely. 4 times, so then I'm just doing division here, right? 32 and 8. So 28. 4 times 28. 4 is another 2 square. We got that 2 square. 28 looks like I can get another 4 out. 4 times 7. That 4 is another 2 square. So altogether I've got 2 to the 6th, and I've still got a 7 as well. So this is 2 to the 6th times 7. Now, once it's in prime numbers, it's a little bit easier to see what to do. You just divide the power by the root. 6 divided by 2, we get 3, remainder 0. So that means this is going to be power 3 out here, and nothing remaining. And 1 divided by 2 is 0, remainder 1. So it's just that. This should have absolute value when you're doing an even power here. Of course, this is just 8, and the absolute value of that is 8. So it's just 8 times the square root of 7. Square root 448 x to the 8th y to the 19th. Look at that. We got the same number again. So that's 2 to the 6 times 7. Can't count on that happening, but it might. Okay. If not, of course, do a prime factorization there. And do the square root of each part. Well, divide the powers by the root. The root is a root 2, second root. So 6 divided by 2 is 3. No remainder. 1 divided by 2 is nothing outside, remainder, power 1. 8 divided by 2 is 4. Okay, no remainder. 19 divided by 2 is 9, remainder 1. And this should have absolute value with its second power. So this is 8, x to the 4th, y to the 9th, square root of 7y. Now, in this case, we can drop the absolute value because it says assume that all variables represent positive numbers. So, if everything's positive, we don't need an absolute value. Of course, we know 8's positive, we know x to the 4th is positive, y to the 9th could be positive or negative. So, but it tells us it's positive, so we can stop there, and that matches what they have as well. So that's good. So there's number 5. Let's go to number 6. Okay, square root of 6 times the square root of 15. Again, think of 6 as 2 times 3, and think of 15 as 3 times 5. Now when I'm multiplying these two things, since they're the same degree radical, I can just multiply what's underneath, which is 2 times 3 squared times 5. 3 squared, square root and the square will cancel, leaves 3. Well, absolute value 3, which is 3. The 2 and the 5 stay left underneath. Absolute value 3 is 3. 2 times 5 is 10. So you just get 3 square root of 10. That's what they have. Good. Number 7. Square root of 2 minus the square root of 5 squared. Just do FOIL. First times first, square root of 2 times square root of 2 is 2. O, that's the F. I'm going to do the L next, actually. That's last times last. Square root of 5 times square root of 5 is 5. Negative times negative is positive, so that's a plus 5. Of course, that'll combine to be 7. Let's do the O and the I. The O, the outer product, square root of 2 times square root of 5 is square root of 10. It's positive and negative, so that's minus square root of 10. And this is also minus square root of 10. So we get minus 2 square root of 10. That checks. 8. Okay, determine visually whether the graph is symmetric about the x-axis, y-axis, the origin. Just look at the graph. Well, certainly it is not symmetric about the x-axis, because if it was, for example, the point here, there would be a matching point down here. It's not symmetric about the y-axis either, because if there was a matching point here, there'd be a matching point over here. It is symmetric about the origin because if we rotate it around 180 degrees about the origin, upside down, actually I think I can do that with my computer screen here. There's a 90-degree rotation. There's a 180-degree rotation, and it looks the same. Okay, so if you can spin it around 180 degrees around the origin, it looks the same. It is symmetric about the origin. So you can see the answer is no, no, and yes. No, no, yes. Okay. Number 9. Determine if it has any of these specific symmetries. So y equals the absolute value of x minus 2. Okay, so if we reflect over the x-axis, we replace y by minus y. So we get minus y equals absolute value of x minus 2, which, if you solve for y, is minus the absolute value of x plus 2. It's not the same. This is different. So no on x-axis symmetry. So no there. Okay, how about y-axis symmetry? For y-axis symmetry, we're going to reflect over the y-axis. Okay, change the sign on x to replace x by minus x. Y equals minus x, absolute value minus 2. But the absolute value minus x is the same as the absolute value of x. So that's the same. So it has yes on y-axis symmetry. Okay, and to do origin symmetry, we do both. We rotate 180 degrees about the origin. Okay, and what you do there is you replace x by minus x and y by minus y. And then you get minus y equals this. Well, this one boils down to the same, but this is different, and so that's ultimately different. So no on origin symmetry. So let's answer the question. Choose the best answer. No, no, yes, and no. So C is the correct answer. Okay, check this one for symmetries. X, y equals 6. Again, we replace x by minus x, and we get something different, or you could write it this way, different ways, but you see it's different. So changing sign on x is reflecting over the y-axis. So no y-axis symmetry. Okay, change the sign on y. That's going to reflect over the x-axis, but again, this turns out to ultimately be different, so no on x-axis symmetry. Make sure I said that right. If you change the sign on y, it reflects over the x-axis. We got a different formula, so no on that one. But this one turns out, if you do both, change the sign on both x and y, which will rotate it about the origin 180 degrees. These two negatives cancel out, and you're back to where you started. So it's yes on origin symmetry. We could try to graph it if you wanted to. That this one is y equals 6 over x, or y equals 6 times x to the negative 1, and we know about power functions that one is going to have origin symmetry this way as well. So that's C. Let's stop there on this video, and then we'll pick up the next bunch on the next video.